All right, let's dive right in. Today, we're pulling back the curtain on the technology that is literally reshaping our digital world, large language models, or LLMs. If you've messed around with a modern AI chatbot lately, you know how incredibly natural it feels. It's easy to assume there's some highly complex, almost human-like brain whirring away behind the screen, right? But in this explainer, we're going to totally demystify that engine. We're looking at the actual nuts and bolts, the architecture that makes these systems process and generate human language.
So it all starts with this one foundational question. How does AI actually understand us? I mean, when you type out a prompt, how does a machine, which, let's remember, only processes ones and zeros at the end of the day, somehow comprehend the nuance, the tone, and the deep context of human language? The answer might actually surprise you, mainly because of how simple it really is. Okay, here's the big secret. At their absolute core, these massive world-changing LLMs, they've just mastered the art of word guessing. That's really it. It's the mathematical ability to forecast the most likely continuation of a given text. They aren't thinking in the way you or I do. They're essentially calculating probabilities to predict what the very next word should be, based on exactly what you just typed. It's a beautifully simple concept, but when you scale it up massively, it produces a remarkably intelligent-sounding conversation. To really wrap our heads around this, here's our roadmap for this explainer. First, we'll look at the art of word guessing. Then we'll go inside the transformer engine. After that, we'll contrast analysts and storytellers, tackle the bias problem, and finally wrap up with fine-tuning and localization.
All right, part one, the art of word guessing.
You know, before we had the massive models we use today, researchers were experimenting with a bunch of early architectures. We're talking recurrent neural networks, long, short-term memory networks, gated recurrent units, and even convolutional neural networks, which actually are mostly used for image processing. Now, these early models were crucial stepping stones for sure, but they hit a massive bottleneck. They had a really hard time efficiently processing long sequences of text. Basically, if a sentence was too long, they just kind of forget the beginning of it. We desperately needed a breakthrough. And that brings us to section 2, inside the transformer engine. Just look at the sheer explosion of innovation here. Right in the middle is what we call the vanilla transformer. The moment this architecture dropped, it completely solved those old bottlenecks. Why? Because it let the AI process entire sequences of text in parallel, all at once, rather than just painfully reading word by word. This meant it could analyze local and global context simultaneously. It was an absolute game changer. From that single vanilla transformer, we got this wild, massive family tree of models you definitely recognize today, like GPT, BERT, and Llama. So what actually makes the transformer so special? Well, it has a secret weapon, and it's called the attention mechanism. This is the absolute key to handling those long-range dependencies in language. Instead of just treating every single word equally, the attention mechanism lets the model selectively focus on the most relevant parts of a sentence. It injects real context sensitivity right into the learning process.
Let's break down how this actually works under the hood, step by step.
First off, each word gets assigned a context-dependent weight, based on how relevant it is to a specific focus word. Next, the model looks at the surrounding words to calculate what we call attention scores. And finally, those scores are used to weigh the data, the embedding vectors. The result? You get distinct, unique representations of the exact same word, entirely depending on its context. This is literally how the model captures semantic nuance. It resolves ambiguities by quite literally paying attention to the most informative parts of your text. Now, because transformers process everything in parallel, skipping that step-by-step reading of older models, they actually have zero built-in sense of word order. None. So we have to use something called positional encoding. This maps the absolute and relative positions of the tokens, the words, and bakes that right into the input embeddings. I mean, think about it. Without this positional map, the AI wouldn't know the difference between the dog chased the cat and the cat chased the dog. It absolutely needs those coordinates to make sense of the sequence. Moving right along to section 3, analysts and storytellers. So transformer models generally fall into two very distinct camps. On one side, you've got encoder-only models. You can think of these guys as the analysts. Their whole job is to extract information, deeply understand the input context, and tokenize it into numbers. They are absolute powerhouses for classification tasks. But then, on the flip side, we have decoder-only models. These are your storytellers. They excel at generating brand new, coherent text based on the preceding context. If you want creative writing or question answering, you call the storytellers.
And this dynamic totally shapes how they process context. The analyst, the encoder model, uses bidirectional context. So if it sees a phrase like, "a man was blank on a riverbank," it looks at all the surrounding words, left and right, to get the deepest possible context. We call this masked language modeling. But our storyteller, the decoder model, it's unidirectional. It only reads left to right to predict the future. It can only use the previous words to guess the next one in the sequence. That strict left to right flow is what ensures the generated text actually makes sequential sense.
But hey, what if you need a model that can deeply analyze a text and creatively generate a response? Well, you just combine them into an encoder-decoder model. The encoder takes the input, creates a rich, continuous representation, and then hands it off to the decoder, which spins up the final output text. If you're doing complex stuff like heavy text summarization or machine translation, this mapping between input and output sequences is exactly what you need. You're basically getting the best of both worlds. All right, section 4, the bias problem. Let's zoom out a bit. We have to talk about bias in LLMs, which really means systematic errors or prejudices in their predictions. According to the source material, this creeps in through a few key avenues. First up is misrepresentation, where certain groups or perspectives are either heavily underrepresented or totally overrepresented in the training data. Then, there's the undeniable presence of historical stereotypes already baked into those source texts. And finally, the human element, the specific design choices, and frankly, the blind spots of the developers building these things. If we leave this unchecked, we're just reinforcing harmful stereotypes, perpetuating discrimination, and spreading misinformation at scale. So, fixing this requires a pretty multifaceted strategy. First is data curation. We have to adopt totally transparent and inclusive practices when we're actually collecting the data. Then, during model training, developers have to actively implement de-biasing algorithms and fairness-aware procedures to correct those skews. And finally, regulation. This is massive. Policymakers have to establish clear guidelines to ensure real accountability when these AI technologies are unleashed into the real world. Which brings us to our final section, fine-tuning and localization. How do we take these giant generalized models and make them useful for highly specific tasks? The answer is fine-tuning. There are 3 main ways developers tackle this. Number 1 is full fine-tuning, where you update every single weight in the model. It works incredibly well, but it's computationally massive. Number 2 is parameter-efficient fine-tuning, or PEFT. Here, you freeze most of the model and only train a tiny subset of new parameters. It saves a ton of computing power. And third is RLHF, reinforcement learning from human feedback. This is where we literally use human feedback to train a reward model, steering the AI so its outputs actually align with what humans want and value. To see how this plays out in the real world, our sources highlight some practical insights for regional experts, using Hong Kong as a prime example. The real local value of LLMs comes from task diversity, using them for highly specific local content generation and translation. But to do that right requires serious localization. These models are trained globally, sure, but they have to be fine-tuned to the unique linguistic and cultural nuances of a place like Hong Kong to actually be effective. And obviously, responsible AI has to be front and center, meaning we tackle local biases and set up firm ethical deployment guidelines.
So we've journeyed from this super simple concept of word guessing, ripped open the hood of the transformer architecture, and looked at the very real-world challenges of bias and localization. This technology is incredibly powerful, no doubt about it. But its ultimate impact, well, that depends entirely on how we choose to guide it. So I'll leave you with this question. As the engines under the hood get more and more powerful, how will we, all of us, users, developers, citizens, actually shape localized, responsible AI for the future? Thanks so much for joining me on this explainer, and keep exploring.